An ordinary differential equation contains the derivative of an unknown function. The ordinary differential equation is an equation having variables and a derivative of the dependent variable with reference to the independent variable. A differential equation contains at least one derivative of an unknown function, either an ordinary derivative or a partial derivative. In particular, an ordinary differential equation has ordinary derivatives. Here, the other ordinary differential equation would be commonly referred to as differential equations. The notations used for the derivative in these ordinary differential equations are dy over dx equals to y prime, d square y over dx square equals to y double prime, d cube y over dx cube equals to y triple prime, dny over dxn equals to yn. Ordinary differential equations have their application in our daily life. One of the applications is to find the equation of vibrations.
My name is YINOSHA from JAKANATHAN, metric number 281146. I will be presenting about the method used in the application of ODE to a real-world problem. Force vibration occurs when motion is sustained or driven by an applied periodic force in either damped or undamped system. Force distribution formula and second-order ODE method is used to solve this application. md square x over dt square, where m represents the mass, plus c dx over dt, where c represents the damping constant, plus kx, where k represents the spin constant, equals to ft, which represents the external force. After getting the general solution, using the method of undetermined conversion, where yx equals to yhx plus ypx, where yhx represents the transit solution and ypx is equals to steady state solution. When mass t and velocity is given, apply it to the general solution to solve C1 and C2. This formula is used in solving this application. Thank you.
I'm Pepe, metric number 279469. I would like to present about problem statement. A 5 kg log stretches a spring 32 cm and comes to rest at equilibrium. The mechanism is attached to a dashboard that produces a damping force equal to 10 times the instantaneous velocity of the mass. If an external force equal to Ft equal to 4 sin t is applied to the system starting at time t equal to 0. What is the transit solution? What is the steady state solution?
I'm Yap Ling Su with the matrix number 281731. I will present about the solution. First, we use formula mg equals to ks to find the value of k. After that, we substitute in the equation and we'll get 5x double prime plus 10x prime plus 5x equals to 4 sin t. To find the general solution complementary equation, we are required to find the root of the equation 5r squared plus 10r plus 5 equals to 0. We get two same roots, which is -1. Then the general solution to the complementary equation is xht equals c1 e power of negative t plus c2 t e power of negative t. Next, the trial solution of xp is a0 sin t plus a1 cos t. We differentiate once to find x prime p and differentiate twice to find x double prime p. Then by using undetermined coefficient, we know a0 equals to 0 and a1 equals to -2/5. Moreover, we are able to find the general solution equals to c1 e power of negative t plus c2 t e power of negative t minus 2/5 cos t. When t equals to 0 and x bracket 0 equals to 0, after solving the equation, c1 equals to 2/5. Then when t equals to 0 and x prime bracket 0 equals to 0, after solving the equation, c2 equals to 2/5. The specific solution is 2/5 e power of negative t plus 2/5 t e power of negative t minus 2/5 cos t. Therefore, the transit solution is x bracket t equals 2/5 e power of negative t plus 2/5 t e power of negative t, and the steady state solution is minus 2/5 cos t.
In conclusion, differential equations are mathematically concepts that show the connection between a function and its derivative. With that, differential equations are useful in many aspects of daily life. From the example of application given by our group, ordinary differential equation, short form ODE, can be used to describe the motion of a dense spring mass system. By using the concept from second-order differential equation, which is an undetermined coefficient method, we are able to solve the previous example of application for vibrating spring. Despite from the motion of spring, ordinary differential equation can also be used in everyday life, such as computing the flow of electricity, the motion of an item back and forth like a pendulum, and illustrating the principle of thermodynamics.